Okay, so you've observed the time versus the number of clips. You have a card here, you have a pulley, and you have weights hanging down here, and the weights of paper clips. So the more paper clips you got hanging here, the greater your acceleration. Okay, that's what we're really trying to get. So what you've done is you've measured the time from, let's say, one point to another, always the same distance, same displacement. Okay? So what we want to do is we want to do a graph of the time versus the number of clips. Of course, the more clips you got, the less the time. So the graph is going to look something like this. Not any attempt to give you the exact curve, okay? But you get the idea, right? So, you know, to get that graph, well, you're going to take data points. You got data points. And you want to draw the curve that best fits your data points. When you get down here to a lot of clips, your time doesn't appear to be changing a whole lot. So, you know, you got to figure out what curve you think best fits the trend. I don't want you to go to Excel and do a fit. You don't even know what function to try to fit it to. And Excel, I don't think actually has one. You'd have to transform your data. We'll talk about how to do that, okay? Because you got a power function with a reciprocal power, okay, and negative power, and it doesn't do that. Okay, so you can't go to Excel and make that curve. Okay, transform the data a little bit, you can, and then you can make conclusions, okay, or draw conclusions. But there's your raw data, okay, and then you're going to take a series of points on your curve. And when you draw your curve, you don't try to go through data points. Matter of fact, it's impossible that your actual accurate curve would actually hit any data point. If your data points were completely accurate, you have the infinite number of significant figures, and your distance was known, and distance was the same as the infinite number of significant figures, the chance, but you have uncertainties in your measurements, okay? Uncertainties in your execution, a little delay in starting it, you know, whatever, okay? Well, each point would be located very precisely, and there's 0% chance anything's going to hit that point, okay? If it's known with complete precision. Now, not everything I just said makes total sense, but we can make sense out of it. So you take, I'd say, 6 or 7 points, 5 or 7, okay? And you figure out the number of clips, which will be fractional, and the time. You just put the points on the curve. You don't look at your scales at all. You distribute the points you think they ought to be distributed in the curve to give you the best information. Of course, you don't have a lot of insight in how to do that, but you still want to think about it, okay? So you get a number of clips here, you get a time here, and you now make a table of, we'll call it N versus, well, T versus N, okay? And then you calculate from that the acceleration based on T. Right? Very easy. You know the distance. Divide that by the time, gives you the average velocity. You started from rest, so the final velocity, because velocity versus time is a straight line graph, has to be double the average velocity. Only when you start from rest and acceleration is uniform. We're going to assume uniform acceleration, okay? So you can calculate the acceleration because you can find the final velocity and then the change in velocity, which you can then divide by the time, right? And I think we understand that. You can use all the formulas. I mean, you can use formulas and stuff. It's really pretty simple if you understand the definitions of velocity and acceleration and the assumption of uniform acceleration, okay? You can just reason it out. You don't need the equations of motion. You don't need to do integrals. You don't need to use big equations, okay? Okay, so anyhow, you get the acceleration versus the number of clips, right? And then you're going to plot acceleration versus m. And you should get a straight line. Probably won't go through the origin, okay? But probably come pretty close. So you're going to get a straight line for acceleration versus m. You're going to do that, and ideally you expect to get a straight line if Newton's second law holds, because force will be proportional to the acceleration. You got the same mass every time. Okay, so the slope of this will be the mass. And then of course when you double the mass, you're going to get a different line. Okay? And you won't have as many data points there. You're going to get the information. That makes sense? I don't tell you too much more than that because I want you to think about what it all means. But that's what the instructions are going to tell you. And what you can do before the instructions are posted is you can sketch this curve and get this and calculate the accelerations. Actually, you can do the whole thing. Okay? It's based on what I told you here. And then we're going to ask some deeper questions about what uncertainties in counting that pendulum and so forth. Remember to report the length of your pendulum so we can calculate period and see if the proportionalities come out consistent with what the SI units tell us. Okay? Okay, so I think you understand that. The other thing is on the incline. Got the ball on the incline, and you've got the forces, which are basically just the weight being the force that gravity exerts on the ball, and a normal force it's a vector, normal force is a vector, and you've got a tiny bit of rolling friction. Which we're going to neglect. We're going to try to measure that later, but it's on the order of 0.1%. Very small. Okay, because it's metal on metal. So what's your net force? Well, you draw your coordinate axis here. Hopefully you remember that. Okay? And why do we draw them here? We draw them here because that's the direction, the x-axis will be in the direction of motion. Okay? The weight breaks into two components. One component equal and opposite to the force, the other component independent of that, and that's what accelerates it. Okay? I'll give you some instructions. It'll tell you that when the slope is small, the acceleration should be just the product of the acceleration of gravity and the slope of that ramp. And you're changing the slope of that ramp every turn by a known amount. Okay? So you can get a graph of acceleration versus slope from your data. And then, of course, how are you going to do that? Well, I'm going to tell you, when that ball falls to the ground, to the floor, you can easily calculate how long it takes to get down there. Okay? As long as the initial velocity is horizontal. Now, you got a little bit of a slope here. That throws things off. We're not going to worry about that for the first pass, but I'm going to want that first pass done for Monday because the calculations are simple. Okay? So we're going to make the simplifying assumption And we'll see why the assumptions don't necessarily work. We'll make the simplifying assumption that it takes 4/10 of a second to fall. Okay? Your velocity at every point has the same component in this direction. We've talked about that, we've drawn it, okay? You have an acceleration in this direction, and things are a little more complicated than this oversimplified version. But we're going to assume and this is after the ball leaves the ramp, okay? We can refine that. It's more like 0.42 or 0.43 seconds in that height. But it varies because the slope varies, and you get a little bit of downward velocity because of the slope, okay? So 0.4 seconds might even be a better estimate than the 0.42 or 43 seconds you would get, assuming an initial velocity in the horizontal direction. So from the distance the ball goes, you can easily calculate how fast it's going. It's got a constant velocity in this direction, right? And that velocity is pretty close to the velocity it had on the incline. Now, because of the slope, you're only getting the horizontal component of the velocity. It's also got a small vertical component. Turns out that doesn't matter much, but we'll analyze later how much, okay? So this is going to tell you how fast the ball was going at the end of the ramp. You know the length of the ramp. You know how fast it's going at the end. So you can calculate the acceleration since it started from rest. Okay? And you just turn the calculation you do for the this situation around a little bit. It's easy to reason out. Okay? I'll give you some guidance when I write the instructions. But what I would recommend that you do then is calculate the average velocity in the ramp, ignoring the fact that it's really a little greater than the average velocity, average horizontal velocity as it falls. Okay? So all you're going to do is divide how far it goes by 4/10 of a second. That's about how fast the thing was going when it left the ramp. That's the bottom line. Okay? We've got to prove that. Yeah, we've got to analyze that a little bit. Okay. But for Monday, get that done. Calculate your velocities. Okay? It's very easy. All you got to do is measure the distances. You got 20 of them or something like that. Okay? The calculation's always the same. Shouldn't take you 10 minutes. Okay? Take you longer to measure than it will to calculate.
Won't we need to measure the ramp and the height of the table?
Tables aren't going to move. Ramps aren't going to change. So you're going to assume. I'll give you the directions. You can measure the ramp. You got a meter stick over there. You can measure where you released it from and how far it is. I'd say it's 58 centimeters or something like that. Because the ramp is 60.8 centimeters. Okay? And a couple of centimeters to get away from the heads of the screws. Okay? So, you know, that's pretty easy. Now, you want to get that done so you can compare that then with a more detailed analysis that we'll be talking about Monday. Okay? Because you get into the projectile motion of this thing, and the ideas are real simple. But the algebra and the trigonometry are just modestly challenging. Nothing's going to give you much trouble, I don't think. But there's some potential glitches in that. And so we got to get the idea first. Okay? Okay, so that's kind of what Yeah, it's kind of vague, intentionally so. I want you to think about what's going on, okay? But you could do those calculations, just preliminary. I'd get those out of the way.